Okay, part C. Here we're actually going to get the data set up and start, effectively describing the data engineering needed to do the earthquake forecasting. So, what is the data? Well, I showed you how I was going to take this 4 degrees of latitude and 6 degrees of longitude and divide it up into 2,400 little pixels, each 11 kilometers or 0.1 degree on the side. Now, the data actually consists of space, event, magnitude, depths, spatial position, and time. Now, it's possible that it would be good to keep it like that, but that's not what we do. We make bins. These are time intervals, which we gather the data together and we accumulate it in bins. Initially, we started off accumulating it in daily bins, but we actually made those bins a bit bigger, mainly for compute reasons, because we're really, remember, interested in multi-year forecasts. We're not interested in what's going to happen tomorrow, because we know that for a large earthquake, it's going to be very difficult to make reliable predictions for that. What we're hoping is we can make a semi-reliable prediction for what's going to happen in the next year or 6 months or 5 years or what have you. We actually, in this analysis, go up to 4 years in the future. And we settled after talking to my colleague John Rundle and about something like 14 or 28-day samples would be good. Now, it's actually not trivial how you accumulate data either into 1 day or 14 days. That's discussed a little later on. And then we, as I say, we're actually going to look up to what happens over up to 4 years. And we actually, in order to train, to predict up to 4 years, we have to accumulate the training data also up to 4 years. Then we have these sequences, which are observation at time t0, and then t1, and then the sequence of a certain length, which varies in our different studies, somewhere between maybe a year in total length. That's 26 intervals, or maybe longer. We chose the length of the sample differently in different times, because that's a hyperparameter. So this is the window length. We have a sequence or window of the data. And then we formed all possible sequences of that length. And that actually means the sequences are not independent, because we have, let's label the 2-week intervals as time 0, then 2 weeks later, time 1, 4 weeks later, time 2, and so on. So we have a sequence beginning at t equals 0, t equals 1, t equals 2, and they're quite long, these sequences. And so the first 26 sequences actually have at least one point in common. Okay, that is just the way it's done. Maybe there's some issue there which needs further thought. Then we have associated with every member of the sequence various properties, and we'll describe what these properties are. And there's lots of choices there about properties, and we also want to associate with every sequence predictions. And that's also quite rich, and it actually differs in the different models. The Google Temporal Fusion Transformer predicts 2-week intervals into the future, whereas the other models just predict big average values. There is something which I spent a lot of effort on, which in the long run turned out to be just life. Namely, if you know the predictions for, say, the next year, every 2 weeks for the next year, you don't actually know the sum prediction for that year, because what we're predicting, when we'll come on to that, because we're not predicting something which is additive, namely energy. We're predicting magnitude, and magnitude is a log of energy. And because of that, things don't add properly, and that's really quite tiresome. Namely, if you add the results of 26 weeks, you do not get the results for a year, because you can't add the logs, and that doesn't work, because magnitude is a log of the energy. All right. So another important, sort of simple issue general to this type of problem is good to know everything, because then you can run the training straightforwardly. Namely, we have no missing data in what we train, which are the properties. However, we can have missing data for the predictions, because in the simple loss functions we use, the loss function is a sum over multiple predictions. So we sum over the 4-year chance of an earthquake and time t equals sequences starting at t equals 0, t equals 1, and so on. We just sum all those values up. And so as we get the sequences start near the end of the training data, we don't actually know the long time predictions, because if the starting points within the last 4 years, we can't predict. We can't train on the 4-year data. So what we do is drop that predicted data. And it's very simple, and I think it's unbiased, and it's straightforward. Technically, we use NaN to signify a missing data, and then the loss function just checks to see if the prediction is NaN. If it is, it doesn't include it. And that works for mean square error or mean absolute error. And because we're not necessarily having all data, we actually average over these different predicted time intervals, and not sum. Okay. Now here's this slide which tells us the subtlety about how you add things together. Well, energy is 10 to the 1.5 times m, approximately. So when we accumulate events, we don't accumulate by adding the magnitudes of the observed data. We accumulate by adding the energy of the observed data, because energy is physical. And if it chooses to break, I mean, you know, this fault has a certain amount, this earthquake will release a certain amount of energy. That's all stored up, waiting to be poured out. Whether it does it in 15 smaller earthquakes or one larger earthquake probably is a choice that it just makes, and is maybe not so significant. What counts is the total energy. However, as we discussed, we really would rather use the log of the magnitude, the log of the energy as the observable, because it has a much more reasonable set of range of values. So we sum events up by summing the energy. Then after we do that, we convert it to an effective magnitude, which we call log energy, by just inverting that equation. Now, when we come to something like depth, we don't average the depths if we have multiple events. We average them weighted by energy. So notice that as we have this rather high power of 10, a small change of magnitude makes a big difference to this weight. So what this tends to do is it tends to, another thing which was sort of a more superficial way of saying what we're doing is, or approximate, is we're taking maximum values. This thing here, log of energy, the sum of these energies log, really means that roughly, unless there are lots of large events, you're just taking the largest event, because it dominates after we take the magnitude and raise it to 10 to the 1.5 power. All right, so I call that either m bin, magnitude of the bin, or log energy. And the one thing we don't fiddle around with is the multiplicity. Multiplicity, which is the number of earthquakes, we just sum up the number of earthquakes. And that's sort of interesting, because multiplicity has some striking structure, because it varies very dramatically as a function of space and time. Something we need to come back, and I'll have another slide commenting on this, is that another 2 slides actually, to explore different observables. This analysis here is done with log of energy, but we probably should look at energy to the n, where n runs between probably 0.25, 0.5, and 1. Now 0.25 is purely mathematical. 0.5, as is mentioned, is a sort of magic value. That makes this called the square root of the energy, is called the strain. And of course, energy to the 1 power is energy. So that's, we know what energy is. It's what drives us all forward, poured out of the sun and things. Now there's this issue of dynamic range. Namely, well, it's pretty important when you're doing deep learning to look at the mean over the maximum. Because if you normalize the data to lie in the range around 0 to 1, it doesn't have to be exactly 0 to 1, but it has to lie in that range because activation functions act on the range around 1. So 1 is a magic value. Now it doesn't have to be exactly 1 because we have weight functions, so we'll multiply something by 23 or 0.02 or something, or even bigger numbers. But if you multiply numbers by 23, a number that was 1 over 23 will become 1, but a number that was 205 will just become enormous. So, or a number that's 0.01 will just not get very big. So it's pretty important that all numbers you're dealing with are roughly in the same range, not drastically different. And as you remark, when you take energy as your variable, you get a 10 to the minus 5 ratio between mean value and maximum. So we do MBin, log of energy, in the results you present. We take energy value, energy weighting for depth, and we sum multiplicity without any weighting. But these are all to be investigated further. Now these plots here sort of compare the magnitude, or this MBin, or energy, log energy, which is the yellow plot on each of them. And we have here we compare various things with this magnitude plot. This is the multiplicity, the number of events of magnitude greater than 3.29. Here is and this is, notice how sharp this is. Here is the log energy. It's got a little blip at this big earthquake here, comparatively little blip, but the multiplicity has a huge blip. And so you can see the multiplicity is a much more dramatic signature of what's going on. And maybe we should actually, that's why I mentioned we might want to do a cut on remove all these low energy, these lower energy events or lower magnitude events, because maybe they're swamping out the signal, because this has real signals. Look at this, signals. And look at this. This is just like, this is not so much of a signal. And here are the various choices. I didn't do e to the 1 because that's dramatic. That's really doesn't look very good at all. But e to the 0.5 is pretty dramatic. E to the 0.25 is not quite as dramatic. You can see the magnitude plot shows up a bit better here. But multiplicity greater than 3.29, that's some sort of measure of a large earthquake and a serious earthquake. And here, the e to the half, these are just have much greater variations. I mean, here we have a huge signal, and you can hardly see it on the magnitude plot. Here's a little comment on the general theory of doing this. If you have an input quantity x in deep learning or any such analysis, you can, as this is sort of empirical and data-driven, we don't, I mean, the theory would tell you energy, because that's physics. Physics is energy. I don't think Mother Nature screws around with the log of energy so much. So, but we're doing mathematics here, and mathematics may not like the physics. So we in general can choose a different function than the natural function. So probably you want to make this function monotonic. So that as x increases, which is important because that's physics, f of x increases. So magnitude, e to the quarter, e to the half, and e to the 1 increase monotonically with e. And as I said, e has this terrible problem that the mean over maximum is 10 minus 5. So there's a conflict in this case between physics and numerics. Other types of problems you can use, you also are faced with this issue, but it's not as dramatic. Like when I did the hydrology analysis, we used x to the 1/3 to try to, you can choose this par. If you have an input, you can look at how it varies, because you want to try to get all the data in a reasonable range, and this is this have a decent dynamic range, and you just choose the par n. And for any n greater than from log n to x to the n to the any positive par, you're going to find a monotonic function. So you can choose that. For some variable data, you might choose x squared if it didn't vary very much. Notice x to the n, if the par is less than 1, it increases the importance of small observables. Small, but maybe small aren't so important. That's why it's pretty interesting to look at. In the case of square root of x, it has a sort of magic significance, because if you go to the counting error that you expect when you observe events, then if you have n events of a certain type Poisson distributions, then the error is square root of n. And if you use square root of x as the input variable to a mean square error and things like that, you will get the correct statistics, because square root of n has an error of order 1. And so if you use square root of an observed number, it has actually better error properties and so it's actually more reliable. But I'm doing it more for just getting a good dynamic range. So there's maybe some science, statistics telling you the right par to take, but as I pointed out, for earthquakes, the right par I don't think is 1. Not least not with current deep learning technology. And this next two plots compare what you have with using magnitude with what you have when you use energy to the quarter, which is the least drastic of these choices. Here is the simplest model, the recurrent neural net, and we'll see these plots again later. These are the results for the prediction of the, here's the results of the training data and the validation data. I'll describe those a little later on, but they're reasonable descriptions. This red thing here, the error is non-trivial, but there's nothing drastic. So, but now let's look at what happens when we go to the next slide, which is either the quarter results. You can see these plots don't look nearly as nice. They're really ugly. There's all sorts of structure which is not seen in the data. So these predictions are yucky. So it doesn't get good answers. Now, this was just one very unoptimized attempt I did. And so I do not see this as the final word. But this means, this is why I went back to magnitude. Well, things like this are why I went back to magnitude. But anyway, this I see as something that deserves further thought. Now we come to another little bit of the data preparation. And this I learned from the hydrology studies. What is a good measure of the quality of your fit? So one good measure is called the Nash-Sutcliffe efficiency. I'm not quite certain why it's efficient, but it's a good number. And it is defined like this: NSE, Nash-Sutcliffe efficiency, is 1 minus, and what is these numbers? What are these things here? This thing here is the square error of the observed value as a function of t minus the mean value over all t. So this is the standard deviation of or the variance, sorry, of the data as a function of time. And here we have the variance of the difference between the predicted value, the prediction measured value, the model value, M is model here, not measurement, and the mean. So we're comparing to see whether the model agrees better than the data than the mean. So here we have, actually, we probably should align these better. Here we have Q0T, here we have the mean, and here we have the model. So Nash-Sutcliffe efficiency of 0 would mean that the model was doing as well as predicting the mean. That's not very good. So NSE of 0 is not a good idea. We actually use the so-called normalized Nash-Sutcliffe efficiency, because the NSE runs between -infinity and 1. We would rather run between 0 and 1, and that is done with the normalized at 1 minus 2 minus NSE. That means that NSE of 1 gives normalized NSE of also of 1, and NSE of 0 gives, which is the, when we do as well as the mean, then the normalized value is a half. So half, we want to be bigger than, significantly bigger than a half to say we're doing well. Now, we all know about faults, at least I think we do. We know there's a San Andreas fault, and there's thousands of faults being measured and located, just largely empirically, just see where the earthquakes are and see how they line up and things like that. And you can find the faults, and I originally thought faults would be very powerful, but I haven't had a terribly good idea of how to use the faults. And also the faults are also sort of overlapping and falling on top of each other and different sizes and shapes and things like that. So we did something quite simple. We took all the faults and divided them into families where faults were close together. We did it rather empirically. And we found 36 fault families shown here. This is our these are our latitude, 36 to 32. Here is our longitude, minus 120 to minus 114. And the different colors with different numbers in them are different fault families. So you can see they're all co-located. I actually told you spatial bags have no co-location. Well, actually, we feed in some co-location to these models by basically putting in the fault family. So the things in the same fault family are certainly close together, sort of correlated. That's the same fault. And some of these faults are quite big. Here we have the San Andreas regions here. And then, but now we use a little triviality that we know that these fundamental theorems saying that you can't actually label cleanly regions in 2 dimensions so that they're all next to each other properly. So we use the space filling curve to label these regions. So they actually, 0 is near to 1, is near to 2, and so on. So this is a space filling curve. And there's lots of space filling curves. We use 4 distinct space filling curves which are fed in those numbers. And so that does mean things are close together. 34 is close to 35, and so on. That may not be the right way to do faults at all. It may be total nonsense. I don't consider our work in faults very definitive. Something to be improved. Next was when you do deep learning or machine learning, you want to have validation, test, and training data sets. Now we use the same validation and test data sets. That may not be, again, the right thing to do, but we did not distinguish test and validation. And we used 80% of the data for training and 20% for validation. And then there's a question of how you define it. Well, if you use the default in TensorFlow, probably you'll get random sample, but that's not good. Because because the input data is correlated, you don't want to take random samples of it. So we used 2 possibilities. One is a temporal probability. You take the first 80% of the time, that's the training data. The last 20% of the time is the validation data. Or you can use space. We take 80% of the spatial points and make them training, and 20% of the spatial points and make them validation. I should say before that we actually, before we did all of this, we chose out of the 2400, we chose 500, which were pretty interesting because they had lots of earthquake hits in them. We used the multiplicity of earthquakes cuts to do that. That's explained in our paper. Of those 500 total points, we're using 400 are training and 100 are validation. And here you see this on this thing. Here, these are the red are the training data, 400 red points. The green are the validation data, 100 validation points. And the gray are the unchosen data. Now, actually, this is some earthquake we plot here some earthquake measure, and you can see actually there's some quite strong earthquake measures which are not in either of these samples. That's because although they might have had a largish magnitude, didn't have a great multiplicity. Again, this is probably something that should be looked at. But I don't think that's terribly bad. I mean, even if we miss some points, we still have 500 great points to look at because there's lots of activity in those points. So there's probably some good data to learn from.